Observatory is currently holding its first fundraiser for equipment and other items of need. So when you're done watching the show, if you wouldn't mind visiting their websites and giving them a few bucks, we'd greatly appreciate it. Anyway, so we've got a full program tonight. So unfortunately, though, the sky this month will be skipped for this presentation. Unfortunately, we've been unable to properly bring Arnold Brody's audio into the room here with us. We've got some sort of technical glitch here. So unfortunately, we're going to have to skip over Arnold's The Sky this month. We will be recording it separately and posting it up on the YouTube channel in the coming days. But unfortunately, it won't be shown live tonight. What this means, though, is our first speaker is our second speaker. Christopher Troup will be talking about Troup will be talking about building and operating an all-sky camera, followed by Ron Macnaughton, who will be talking about comets, travelers from far and very far, followed by Frank Dempsey with recent additions and notes about the Toronto Centre's Telescope Loan Program, and then I'll be finishing off with the announcements. Just a quick show of hands, is anyone here for the first time? Welcome. Okay, and we'll get started with Christopher.
Thank you. Hey, folks, I'm Chris. This is a render of Model 7 up at the CAO. And that little thing that's sticking up at the back is an all-sky camera that I built a couple years ago and recently moved it to the CAO. Had a bunch of questions about it, and so I figured I'd do a quick talk about how I built it and why you might want to build one too. So it's some obvious stuff out of the way first. An all-sky camera is a camera that's designed to record the entire sky. So it's got a big fisheye lens on it that tries to capture the entire sky rather than a telescope, which may zoom in on a very narrow area. I'm obviously interested in the night sky, but it does do daytime stuff as well. So if you're interested in looking at the underside of daytime clouds, you can do that too. I built it because I'm an imager and I wanted to know when and where clouds were coming in. So that's why I built it for at my house. I used to operate my telescope remotely from my basement while it was set up in the backyard. And it was useful to be able to see when clouds were coming in and if I should pause an imaging run instead of having to go outside and figure out why I lost guiding or something. I still use it for that, but I've also learned over the couple of years of operating it that you can get amazing time lapses and other awesome stuff out of an all-sky camera. And so I thought maybe I'd share some of those things with you and hopefully convince you to build one, and then we'll go through maybe how you might build one as well. So this is a pretty cool one. This is from the Aurora back October 10th, I want to say. This is a time lapse of the night. I was lucky enough that I was up at the CAO that night, and so I got to see this. And it's pretty cool to be able to see the whole night time lapse, put out like that. I'll let this run through until morning. That's obviously a pretty atypical night from that perspective. This is kind of a more typical night. This is just a nice clear night up at the CAO before the big stupid moon comes and ruins everything. So I have to shut down an imaging run. Okay. But I promised you I'd talk about how to build it. And so I thought I'd first start off talking about some of the design considerations, the things that I wanted to worry about when I was building a camera and, I wanted to leave it out 365 days a year. So obviously, primarily, we're worried about rain and dew from outside. We want to make sure that the equipment inside of it is not particularly expensive, but it's enough. You don't want to be replacing it on a regular basis. Internal moisture and humidity turned out to be the main demon I had to fight. So we don't want humidity trapped inside the enclosure and crashing out of the air as dew that forms on the internal surface of the dome, which blocks the view of the camera. Turned out to be the hardest challenge, and we're going to spend a bunch of time talking about some of the strategies on how I used to get rid of that problem. We obviously need to power the camera, and we need to extract data from the computer, so we need power and data to the camera. And then heat as well. We do want the interior of our enclosure to be a little bit hotter than the outside environment, but we don't want it so hot that the computer goes into thermal throttling or something like that. And the camera sensors, obviously, their noise floor goes up as they get hotter. So you want to keep the sensor as cold as possible. So those are the things that we're worried about. This is what I built my camera with. So the computer inside is a Raspberry Pi, a Pi 4B or a 5, strongly recommended. You probably use an older Pi if you have it lying around, but the software that we're going to use really wants a Pi 4B at the oldest. A ZWO camera, in particular, they have two models. The older one, I guess, is the ASI 178 MC, which is their sort of like their all sky camera from last year. They have an improved version of it up now, which is the ASI 676 MC. Both of them are, you can use them as planetary cameras, but they're really excel at all sky cameras. And in fact, they come with an all sky camera lens with them. If you buy them, they will come with a lens. And so coming up next, you will need a CS mount fisheye lens. The ZWO cameras, as I mentioned, they come with a 170-degree lens, and it's good. There's nothing wrong with it. I upgraded it to a 185-degree lens that I got off of AliExpress, just because I really wanted like horizon to horizon. Not sure it was worth it, but I own it now, so it stays installed. Obviously, we need an acrylic dome. A glass dome would be better, but they get pretty expensive quickly. The enclosure itself, the instructable I followed to build it recommended using ABS pipe, and that's what my first version used, and it works really well. Eventually, though, I 3D printed an enclosure because I wanted some extra features. And the software that we're going to use is up on GitHub. It's freely available. It's open source. And we don't have time, obviously, to go through the installation today. But once you acquire the software on the Raspberry Pi and you run this install command, it will walk you through all the configuration. One of the things that you'll want to make sure you have handy when you're installing is the longitude and latitude of your site, because that turns out to be fairly important for the way the software configures itself. So don't put in fake coordinates like I did the first time I installed it. Okay, so this is a render of the all-sky system, but obviously the interesting bits are on the inside. A cutaway view allows us to see a bunch of the relevant details. The enclosure is actually open at the top and bottom for access. A dome and flange cover the top to make it weatherproof. But we want to be able to take the top off because you need to focus the camera. That was one of the complaints with the ABS design that I had, was that I actually had to take the whole guts out of the enclosure to be able to focus the camera, and inevitably that was a pretty painful process. So having the top being able to be taken off is pretty critical, I think. The bottom screws it closed via an opening, and cables come out via a cable gland that allows us to pass network or power through. And then the computer and camera are mounted on an internal mounting frame. So I said we're going to talk about weatherproofing. There's kind of two options. One is arguably the right option, which I immediately didn't choose, which is to cycle air through the enclosure itself, and actually like draw air in with a fan, blow it over the electronics and camera and dome, and be able to vent it as well. You probably need a dew heater in that case to keep dew off the internal, the dome interior, but you get things like cooling for the computer and cooling for the camera, and that would be really, that's a beneficial thing. But it does complicate the housing design because you need fan intake and venting, and you also need to be careful you design it in a way that rain isn't able to infiltrate. And I was really lazy, so I didn't want to complicate the enclosure. The other option, which is what I chose, was to hermetically seal the system so it's completely closed. And so basically we're going to seal up all the air, make it moisture tight so that no external rain can get in, and then just cram a desiccant can in there to pull the moisture out of the air internally. And so what that might look like is, if we look at the sort of a zoomed in view of the top of the dome flange, when it's cut away, you can see some of the weatherproofing feature that we've got designed into it. The dome itself sits in a groove and then is affixed to the flange with RTV silicone, which gives it a nice strong bond and makes that waterproof. We have some venting cut into the flange as well. If you can see those little circles, allows some air exchange so that the heat that's coming off the computer is able to heat the dome and hopefully keep some dew off of it. And they also, we'll see in a little bit, those also work as retention fingers so that the camera isn't pushed too high in the dome. But of course, we need to make sure that is no water can get in through there. And so an O-ring sits inside of the track of the screws that blocks any moisture that tries to migrate over the lip of the flange, or more importantly, actually through the screw cavity. So a previous version of this, I had the O-ring on the other side because I'm an idiot. And moisture was actually able to get in through the screw holes and migrate into the enclosure through there. So the internals of the system, if we look at the internal mounting frame, the camera's mounted at the top of the frame, the computer's mounted on the side. You can't see the other side where there's a big desiccant can that's double-sided taped to it. There's venting holes, again, at the top of the frame, so hot air from the computer can access the dome airspace and keep moisture off the internals. Don't forget to leave space for USB camera, so USB cable from the camera, so we can get the actual data off of the camera. And that's basically it. The mounting frame is pretty simple. Inside, the internal frame is held in place via an interference fit. The screw plug pushes the frame up against those retention fingers that are on the dome flange, and that holds everything securely. Another design iteration that I took over time, but I made after the fact, but there's actually an index that's built into the enclosure itself that interfaces with a groove on the mounting frame. The reason for this is, one, it makes assembling it repeatable so that you always know where north is. In particular, it's because as you screw in the bottom of the plug, it wants to turn the internal mounting frame. And so having that index that retains it in place allows determining where north is way easier. Design-wise, that's really it. Obviously we want desiccant in there to make sure that any moisture that's in there is absorbed. You should think about how to power it. I use PoE, so power over Ethernet, so I could get network and power through a single Ethernet cable. The problem is that doesn't provide a ton of actual available power. So if you are going to have an internal dew heater, then you're probably going to want to provide 5-volt power through some other mechanism. But it was convenient for me because I only wanted to run a single cable to it. If you're 3D printing the housing, choose a good plastic. It is going to be outside baking in the sun every day, so UV damage will accumulate very quickly. So spray paint it white to reflect light to help cool it and provide some nice protection against UV. And yeah. And the other thing is the dome is a magnet for poop. Birds love pooping on these things. And so if you treat it with Rain-X, at least when it rains next time, it'll wash it off in some way. All right. So what are the actual features of the camera? So the software that we installed is pretty cool. It provides a couple things out of the box. One is a kilogram, and I realize this is really hard to see because this picture is actually a mile tall. But a kilogram basically is a way of looking at the entire night in a single image. So it takes a 1-pixel vertical stripe through the center of the image every 60 seconds, and then arrays those horizontally over the course of the night. So you can sort of see like what a continuous view of the entire night looked like had you been looking straight up. And it's nice if you just want a quick glance at, hey, like, were there clouds last night or was it relatively clear? It's a good way to look at that very quickly. Star trails are pretty popular. Everyone loves star trails. I don't know what they're used for other than looking pretty, but they are pretty. And finally, some other fun things is the software has meteor detection, which you can enable. This particular one wasn't caught by the meteor detection. It was during the aurora. It was reported on the forum, so I went back and looked in the raw images and found it, and that was pretty cool. And then finally, the other thing, I shouldn't say finally, but the other thing is that the public website that comes with the software is pretty neat. I've got mine published at obs.minichake.com/allsky. And so if you want to see what the skies above CAO are looking like at any given time, you're more than welcome to visit there. It's permanently installed above Model 7. So yeah, feel free to use that. And the software also has a management website, which allows you to kind of tune the relevant parameters, the gain and the exposure lengths and all those other types of things, and a bunch of other features. But fundamentally, that's it. That's all I've got. I don't know if we have time for questions or not. Yes. Is that better?
Any questions for Chris? Chris, could you give me an idea of roughly what the whole system costs? Not the dome, but the all sky.
Yeah, I mean, the cameras. So a Raspberry Pi, an older model Raspberry Pi, I think will run $60-ish, $50, $60. And the camera, I did go out and buy a camera for it. I think it was, call it $250, I think, for a camera. Frankly, I don't think I would spend $250 to do that. If you have an old guide camera or an old planetary camera that's lying around, this is a great use for it. Instead of it collecting dust in a drawer somewhere, stick it in an all-sky camera. You could build these pretty cheaply if you want to, for sure.
So some questions about calibration of this thing. So first of all, can it quantify the background sky brightness at night? And if yes, then how easy it is to calibrate, and does it keep the calibration well?
Yeah, that's a great question. It's something I've been playing with. So the software doesn't do that natively. I do have a cloud watcher which has a sky quality monitor on it, and so I do have a fairly reliable measure of sky quality available to me. And I've been playing around with sort of correlating that to the image. In particular, I've been just saying I've been working on playing with some machine learning models that run on top of that and basically say, hey, there's a cloud that's coming in. It's going to pass over the area you're imaging in 5 minutes or whatever. Why don't you stop exposing for a few minutes and let that cloud go by? And it seems to provide a pretty good estimate of sky quality as well. But this is a toy at this point. It's not something that's generally useful, but it's something I've been playing with.
So did you notice any variability in your difference between the camera and sky quality meter?
It's pretty constant, honestly. So the exposure lengths do vary. The software hunts for a certain exposure level. In practice, that means on a dark night, when the moon is down, I've got it configured. It'll max out at 60 seconds of exposures. And so as long as the exposure lengths are constant, it's pretty reliable as far as measuring the sky quality.
At the CAO, you have power, but if you have a more remote location, like a cottage or something, what's the total power drain? And if you want to set it up with a solar as opposed to something like that?
Yeah, I think the Raspberry Pi draws only something like 2 watts. I don't know what the camera draws, but it's a fairly low powered system. I have never run it off a battery, but I know other people do run it off of batteries. They'll stick a Jackery in a waterproof container and run the camera for a week or 2 off of that. It's a pretty low power system in general. It's the other thing I will add is, I have network connectivity as well, and so I'm able to pull images and publish them to the internet in real time. You don't have to do that. The images are stored on an SD card, and so if you have a remote site that you want to leave the camera there for a week and then come back and grab the card and see what happened afterwards, you can do that as well.
Chris, you mentioned that you have the camera installed in your backyard earlier.
Mm-hmm.
So how do you run the power to power the camera in the backyard? Do you run the cable? Do you dig the ground? Things like that?
So unfortunately, I'm a giant networking nerd, and so I have a bunch of expensive networking equipment, and the switches I have at home and at the modal all have power over Ethernet. And so I wanted to use that, and so the power comes to the camera, the whole system. The power and networking come over a single Ethernet cable. It was one of the reasons why I wanted to use PoE, is so I could just run one cable from one corner of the garage, all the way around up to the roof, up to a pole above the garage, instead of having to find a way to route power there as well. So yeah, it's just over an Ethernet cable. Again, I would argue that is wild overkill for what is needed. If you were building this yourself, I would just plug in a 5-volt power adapter and call it a day.
And seeing no more questions and nothing coming in from online, Chris, thank you very much.
Cool. Thanks, folks.
And we'll take a short break for fun facts while we switch over to the next presenter.
Some of them came even further away. So if I figure out how to. Yeah, okay.
Because I can only see one hand.
Okay, okay, good, good. Good evening, everybody. I find comets so fascinating, especially given how far they've traveled. And I say very far because some of the comets are amazingly distant. I'm going to start with a few pictures. Comet Halley rhymes with Sally. In 1910, there was a good apparition, and they took this picture. It must have been, they didn't have computers to control telescopes in those days, so they must have had some motor that would drive the sidereal time to follow the stars. And then they had to have an extra motor to push it a little bit so that the comet stayed in view. And they probably have, I don't know what emulsions were those days, maybe ISO 200 or something or other. And they had to have a long exposure. Can you see how far the comet has moved by the star trails? The brightest comet I ever saw was Hale-Bopp, and we saw two comets in a row. This one was visible in 1997, but it was discovered 2 years earlier because it was nice and big, and it was visible a long way out. I had recently started astronomy then, and I was too stupid to know that with comets, you never bother looking at the nucleus in high power. But when I looked at it under almost 200 power, there's a pinwheel pattern at Hale-Bopp, and that just blew me away. And I wish every time I observed, I'd made a little sketch and maybe do one at the beginning of a session and one at the end. And I think I could have seen how quickly it rotates, if that's caused by rotation. But it was really a magical thing to me. And I encourage you, if there's ever a bright comet, try that. If you look at it from the side, you wouldn't see that pattern, but it just happened that Hale-Bopp, the axis of whatever caused it, was in view. This is my favorite comet. Yakutaki came, it was discovered in the second half of January. And when you see 1996 B2, that mean was discovered in the second half of January in 1996. And that's how the system works. The letters go up as the months go on, as the half months go on. What I loved about it is the view was about half the sky. So if the comet nucleus is here, it went all the way halfway around the sky. It was just stunning. And I decided I would take one of my first astrophotos. So I had a telescope with no motor to it, just twiddly knobs. And I decided, well, I'll just try a picture. So I bought a roll of slide film, and I could only buy 36. You know, they had massive rolls in those days. And I looked through my telescope at the comet, and it moved compared to the stars behind it. And I was using the twiddly knobs thinking I'm tracking it, and I tried to be as careful as I could. And the comet patterns were jagged all over the place. It was a complete disaster of a photograph, but Dominic Derrick did a better job. I made this talk originally, and I told Paul I would give it because he asked for someone to fill in. And in 2012, another comet like Hale-Bopp was found a long way away, and I'll explain how they know how far away it is. And this was taken well before it got into close to the inner solar system. And Paul Martfield had to take 7 images of 2 minutes each. I don't know whether he used film or this or electronic. It was 2012. And with a big telescope, and this was really faint, and it got much brighter later on, but it ended up being a dud. The final comet broke up when it went around the sun, and it really wasn't that pattern that good. But apparently a whole bunch of comet experts were asked, what do you think about it? And a lot said, well, comets are unpredictable and we'll see. And one scientist said something like, oh, it's going to be awesome. It might be as bright as the full moon. So guess what the headline was? Anyway, it definitely wasn't, but I made this talk for that, and I've tweaked it a little bit for this talk. This comet, I saw it at sunset, and I remember looking at it, and just after the sunset, still in the bright glow, I could see the comet there. It was stunning. But what comets do is when they go around the sun in perihelion, they often are visible in one hemisphere before and the other hemisphere after. And the poor people in the southern hemisphere had to watch this. I mean, don't you feel sorry for them? Mind you, we were lucky of other things. So that, I didn't see it personally. And actually, I heard some of the best professional astrophotographers in Canada, Terence Dickinson and Alan Dyer, said, "Oh, do I ever wish I'd flown to the southern hemisphere for that?" But they didn't, and it was just stunning. So what are comets made out of? If you ever talk to a school group, something neat is to build a comet. And JPL has a video of this. And you basically have water and dirt plus some starch, syrup, vinegar, alcohol, ammonia, whatever you want, and dry ice. And it's easy to pick up. You just put it in a cooler. I didn't trust the dry ice in my car. I don't have a trunk like it's one big unit. So what I did is I drove with the windows open. Unfortunately, no policeman stopped me because I was drunk or anything. But you've got to be careful if this is in a room. It's better to let it sit for a day, and that gets it a little bit more punky, because what you've got to do is pound it with a hammer and break it into pieces, and then you mix the water and everything together in a bag with insulated hands, gloves, and you get this. Just to show of hands, has anybody ever seen somebody make a comet in front of Freddie? It's really neat to do, and the kids are so engaged because you hold it out to them and they can feel it. Well, I don't want to touch it that cold, but anyway, it's a neat thing to do. And I suspect these people added some ice cream as well, but I'm not sure. But that's not that accurate a view of comets. I thought it was perfect. They are made of dirt, water, dry ice, all frozen together. But comets actually reflect very little light. They're almost as little as this poor bird that is about to be dawn treated to get rid of its oil. The other thing is most comets have an irregular shape like this one. The ones whose pictures I've seen are not round like anything. They're typically this sort of shape. And I don't know it would be possible to add enough black paint or something rather to the mix or something else and to shape it to be more like that. But it's pretty accurate as a view of what a comet is. I'm going to describe two missions, and I wondered about adding the Rosetta mission that actually landed on a comet. And I said, no, I'll leave these two because they're both neat, but later on they landed. Unfortunately, the lander, there's a saying, for want of a nail, a horse was lost. And for want of a working thruster to hold the lander onto the comet, it bounced and it ended up getting caught in a crevasse, and it lasted until the batteries wore out, but the solar panels didn't provide energy. And that's too bad because they had awesome experiments planned, but c'est la vie. Anyway, deep impact. No quarterback, even the best, can aim as well as these guys did to hit the comet. So the comet's moving. It's not necessarily moving in the direction of the tail, because when it's leaving the sun, the tail is pointing in the direction it's moving rather than behind it. Anyway, the mothership fired this lander that took some pictures and sent it back, and the mothership took all sorts of pictures, and let's see if this works. Boom. Oh, it came again. So they did all sorts of measurements of what happened when it landed, and they came to the conclusion that it was soft as a snowbank, which was later refuted by the Philae lander that Rosetta had, and it had less water, more dust, and more organic chemicals than expected, but they actually did that experiment. One model of a comet is that you have a layer of tar carbonaceous material around the outside, and you have different jets that squirt chemical, like dust and dry carbon dioxide and water out. And so that's how a comet works. And eventually it gets smaller. And maybe that explains the pinwheels from Hale-Bopp. and also the striated pattern of that the poor people in the southern hemisphere had to watch. I'd love to have seen that, but c'est la vie. Second mission I'm going to talk about is Stardust. And what the Americans did is they sent this through a comet tail, and they collected the bits of dust in a very interesting way. And then this ended up landing in Utah, and they did their research and they came to this conclusion. So here we go. They made a chemical called aerogel, and it's almost only a little bit denser than air. So it's really fluffy. And they put this in the device, and they went through it, and the particles, instead of hitting something solid and then they'd crack open, they slowly slowed down, so they were able to get individual particles that haven't been damaged. And so they got them, and they did all sorts of tests, and they were surprised that some grains had CAIs. I didn't know that term either. Calcium aluminum inclusions are something found in meteorites, between other things. And when they do radioisotope tests, they're able to date it. And 12 years ago, the oldest thing in the solar system was this 4 billion and a bit years. And when I looked it up to research for this project again, it was the same year. So that research hasn't changed. I would have thought they might have updated it, but that's it. Now, a key thing that I'll get to later is that CAIs only form in a hot place. And that's a problem that, to my knowledge, hasn't been resolved, 1300 K. How do comets form? All right, so this is a picture of the star Beta Pictoris, and they're very carefully monitoring it. It's a relatively young star, and I'm just going to try and illustrate here with my hand. When you have a nebula forming that slowly turns into a star, there are molecules moving all over, but it turns out there's a net rotation in one direction or another. It could be like this or like that. Now, what happens with that rotation is you sometimes get particles going up if the plane is like this, and sometimes go down, and when they hit each other, they sometimes collide and they end up going mostly straight. And this is a mechanism for things to flatten. And in my opinion, most astronomical objects are either spherical or roughly spherical or flat, like Saturn's rings, galaxies, solar systems, etc. And that's the factor behind it. Anyway, they got collected this. This is from stardust, and you end up with small particles, and electrostatic attraction happens. Like there's very little gravity between small things, but these attract together to form bigger things. And over time, when these things are drifting around, they get bigger. And eventually they reach a size where they have gravitational attraction. And as everything is slowly drifting around, what they do is they gravitationally attract and join each other. And you end up getting the basis for solar systems and stars and whatever. I tried to do more research on that, and I didn't get as much information as I wanted. Now, in any solar system, once the star ignites, it's going to be hot in the inner solar system, but colder further out. And it turns out when you're in the inner solar system, the rocks and metals condense like Earth, but the hydrogen compounds, including our favorite, water, stay vaporized. If somebody pours some water over the moon, it's just going to vaporize and go into space. Similarly, when a comet with water vapor in it goes into the inner solar system, it's going to sublimate into space, and we see comet debris. Now, when you're further out, it gets colder, and then the hydrogen compounds do collect. So the message there is that it's far away that it's cold enough for comets to form, but the CAIs, calcium, aluminum intrusions, need the heat. So how could you get those things that are close to the star all the way out to where the comets are? And to my knowledge, there's no answer yet. What makes the tail? Well, there are two tails, actually. Has anybody seen both tails of a comet? There's a blue one that is an ion tail, and it's pushed away by the solar wind, and it goes straight away from the star, or our sun, of course. But there's a dust tail that is pushed by radiation pressure. Every photon going through has a little bit of momentum, and when it hits a dust, it nudges it a little bit. Now, this doesn't perfectly follow the distance away from the sun, but it's the tail that we most can see from the dust. And as a comet approaches, the tail gets longer as it gets closer to the sun. And then it turns around and it goes back. And the key is when the comet goes away from the sun, the tail is ahead of it. And lots of people think the tail follows the sun, but not so. Don Macnaughton gave a talk once. And I was watched him. I think it was Neath, but I'm not sure. And he just looks like a friendly guy, and he came across as a friendly guy, and he loved spending hours looking through his scope. Now, I think at Neath there were some mounts that were not that much money, $30,000, $40,000 for a mount. Now, do you think he spent $30,000 or $40,000 on Home Depot to get his mount there? What do you think? Yeah. He put this together and he observed 7,000 hours looking for a comet before he found his first one. And that would be 3 years at 6 hours a night, every night. Wow. Talk about commitment. And it took him the same amount of time to get his second comet, but then it was less time to get his third, fourth, up to 12. He found 12. Unfortunately, he passed away a few years ago. When you find a comet, you look for a fuzzy patch that doesn't have stars like a globular cluster or isn't on the Messier list. And what you do is you look for it to move. And then they suggest you call a friend and say, I think I found a comet. Could you look at RA this and DEC this? And the friend will fire up his telescope or her telescope and look at it and say, yeah, I see it as well. And they encourage the reports. But they said that 4 out of 5 reports of a comet are duds. And they've got to check it. Now, I'm going to talk a little bit about how objects move around the sun. They follow what's called a conic section path, and you can make a conic section by cutting a cone in a certain angle. If it's not that steep, it's an ellipse. If it's parallel to the side of the cone, it's a parabola. And if it's closer to straight up and down, it's a hyperbola. And the different paths depend on different properties. I used to teach high school, and my grade 12 physics students were to draw a diagram of a real comet where everybody had to pick a different actual comet. And they had to draw an ellipse to show the shape and also draw the circle for the Earth's orbit. You use string and you just wrap around 2 pins, and that makes it work. Now, 1 pin is going to be where the sun is, say the yellow one. The other one is not really a big point in the solar system, but if you're in a room that is shaped like an ellipse, make sure you're not sending it one focus and you dish your boss who is standing at the other ellipse or other focus, because the reflection will transmit the little talk a long way. Now, a key concept in any conic section is eccentricity. And the major axis is the long direction of an ellipse. And basically from the center of that axis, the pins are 54% of the way to the outside. So if the eccentricity were 0, both pins would be the same place and it would be a circle. And if it were bigger, anybody know where this is? Pardon me? Yeah, that's a DDO. They had a big conference there, and they made this to be the shape of a specific comet's orbit, and the eccentricity here is 0.85. So that means from the center of the ellipse to the sun is 85% of the distance to the comet orbit, which is the curve going around it. And that is comet 2P Encke, which obviously was the second periodic comet to be found. And its Q is the perihelion distance. And if you look at the distance between the sun, which is that dot, and the end, it's about 1/3 of the distance to the Earth, the astronomical unit that I've shown. And I equals 12 degrees. Anybody want to guess what I stands for? In terms of an orbit? Sorry? Yep. The inclination, our planet is on a flat plane with which the sun is also in it. But a comet also is on a flat plane that is usually tilted compared, and it actually goes on that plane, and the I is the inclination or the distance between the two. Now, there are a couple of other angles that are part of the defining an orbit, but I'm not going to go into them. So here's Comet Wild 2. Its inclination is 3 degrees, so it's almost in the plane of the solar system, so it's easy for us to reach it and get back home again. So it's been used for a number of missions. 1.6 AU is about the distance to Mars orbit. My favorite comet, Yakutaki. And what was magical about it, I don't know if I can point. Yes, can you see the cursor? Can you see the cursor? On March 25th, remember it was only discovered in January. On March 25th, this comet, just a minute, what am I doing wrong here? This comet was fairly close to Earth, so it was moving quickly compared to the distant stars. And like I say, 90-degree tail, just stunning. When it went past perihelion, then the people in the southern hemisphere didn't get as good a view as we did, but they can't get everything, right? Sorry, I couldn't resist showing you another picture. So in summary, if the eccentricity is less than 1, it's going to be bound. If it's exactly 1, then it's a parabola, and it, in theory, starts from infinity, goes around the sun, and then goes back out. And there are a number of comets with that. And if the eccentricity is greater than 1, it escapes. So the path of an object around the sun is defined by 6 numbers or elements. I talked about perihelion distance and eccentricity. Eccentricity gives the shape. Is it round or is it long and narrow? Date and time of perihelion, inclination, and the 2 angles that I'm not going to explain. All right. Is there a separate mic I can hold? Oh, I can just take this off, right? All right. So if I can you hear me still? All right. I have 2 pictures here that I took when the New Horizons spacecraft went to Pluto. This one was followed 2 days later by this one. And there's a dot that is Pluto on this side in the upper one. And 2 days later, it's on this side. I don't want to spend a lot of time on this, but did anybody look at it and see the dot that has moved from one side to another? And if you just tell me where to move the pointer. Okay, are you telling? Okay, so you're in this one. So where do you want me to go? Left, left, left. Ah, that was Pluto the first day. Now, did you find it in the second picture? So where do I go? Well done. Well done. That's a fun thing to show kids, by the way. They get so excited, me, and they really enjoy it. And to actually see a planet move in the sky. And I felt like when I saw Yakutaki move compared to the stars. That was such a wonderful moment to me. Okay, it's still on. Then what they, unfortunately, I only did 2 measurements. I wish I'd done 3. Because if I had done 3 measurements, there's some formula, I don't know what it is, but they actually find the 6 elements of the orbit, and it would give a rough idea of where that object is going to end up moving. It's a little more complicated by this. But then what they do is they say, well, okay, this says the comet's going to be here in 2 months, but it also says it's going to be back here 2 months ago. And then they can find images for that, are taken, like there's this file of images of the DDO. I don't know if it's still there or not, of old images. And they can find an old image. Oh, we didn't realize, but that's the actual thing we've seen. And when they get more data, they get a more accurate measurement. Now, I took, for my research for my talk in 2012, a dozen years ago, I downloaded a list of all the comets with all the orbit element data. And I processed it with Excel, and I made a graph. And at the bottom of the graph is the eccentricity. So at 0, it's round shape. And at 1, it's a parabola shape, and so on. And the second is inclination. And I've got names of a number of them. I just point out the periodic comets that are orbits of less than 200 years, they have a number with P and then the name of the person that discovered it. And it looks like Hartley had discovered more than one. The other objects, and I didn't have space to do it all, if it's one that just comes out of the blue and not periodic, they have a C/ and then they have the year, and remember that's the second comet in the second half of the year, and the Yakutaki is this Japanese guy that found it. Now, it turns out that there's a whole group of comets down below that have periods of about less than 200 years, and they're called periodic comets, and they have a problem with them. Every time a comet comes close to the sun, it gives off a tail. And what's the tail made out of? Stuff the comet was made out of, right? So the comet gets less heavy, and the estimate is a comet can last a few hundred orbits. Now, a few hundred orbits of comet Halley is 15,000 years. Now, that's a long time for me. I'm not going to live even to the next apparition or appearance of Halley. But cosmically or geologically, that's just a drop in the bucket. So fairly soon, this comet will not be put on a show anymore. And so where do new comets come from? And a Dutch astronomer, Gerald Kuiper, said, maybe there's a series of comets stuck way out there, far away. And he figured, given that most of these comets are in the orbit of the solar system, that it would be relatively flat, and it was ended up calling the Kuiper Belt. And this is something like 20 to 50 AU. But there are other comets where the eccentricity is almost 1, which means that's either a very long orbit path or infinitely long. And those comets come from what they think is the Oort cloud by another Dutch astronomer. They seem to like comets. And it's much further out, and it's completely spherical. There are comets from all directions, and comets like Yakutaki with an eccentricity that's almost 1, they come from way out there, very far away. And so that's our pattern. How do the distant comets get in? Well, there might be other objects there, maybe a big planet, but even if there aren't, if it's a small object, and if a comet goes just in front of another object, it's going to attract the other object that gains energy, so the comet loses energy and goes inward. Now, if it turns out it goes behind another object, the comet gains energy and the planet or whatever it is loses. All right? So it doesn't gain. But what about a comet that comes close to, say, 20 objects and everyone just in front? So it comes across, it bends in, comes across again, it bends in, and it keeps getting deflected inward. Now, that's pretty unlikely, but it's we're talking about trillions of comets and a lot of events. So maybe that's how they come in, or maybe it's just one star, or maybe one planet it hits. So my last question is, do comets travel to us from beyond the solar system? Believe it or not, they've found comets around other stars. This Beta Pictoris, they've looked at it by, telescopes and monitored the brightness. And it turns out when a comet comes, there's sometimes when the brightness of the star drops in a certain pattern that matches what they thought comets would, and it ends up being, they figure it's a comet, and they found 30 comets around this star, including a bunch where they happen in a row, blunk, 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 and they figured there may be a comet that was split apart, which comets do, and there were several tails in a row that went across the star, but there are comets out there. Now, if you look at the bottom right corner of the graph, there are a few of them that have an eccentricity of above 1, which means they're hyperbolic. And probably these 4 comets, again, this is a dozen years ago, the eccentricity is big enough that they're going to have enough energy, they're going to go, but maybe they're going to go near a planet or somebody that then they don't leave. And we don't know because we can't see comets when they're, 300 astronomical units away. Now, there have been since then some interstellar objects. The Ison comet is a little bigger, and whether it actually leaves the solar system, who knows? They include Voyager 1. I took this from Wikipedia, and it's 1.2. The Voyager is 3.72. Now, it's not a comet. It's being fired by a rocket. Oumuamua, you've all heard of Oumuamua, right? And Oumuamua is 1.2, and it definitely came from another solar system. And Borisov is 3.36, and it also is definitely an exocomet. Now, somebody made this graph with, there were different dates, but they put both on. And you see how Oumuamua comes from north. It went close to the sun, so it has a sharp bend, and it went out. And unfortunately, it was only detected when it was leaving. If we had detected that when it was coming in, imagine the data they could have got about that object. But it was madly leaving when we finally got. Borisov is this comet here. It was a much further away from the sun at perihelion, and it bent only a little bit, but it's definitely an exocomet. So, oops, I meant to say something. Astronomers have only found 2 objects that are definitely exocomets. So is it going to take a long time to find the next one? Maybe not. You probably heard about the Vera Rubin Observatory in Chile, and it's going to do a survey of the sky and get amazing information. And the head of communications held up a model. This is not the real chip. In my computer, the chip is about this big, or my camera, is about this big. Look at how big that chip is. It's the biggest one. And they think, oh, that's the full moon that they put on it. And they figure they can take the visible sky from that location every 3 days. And they're going to be able to then get computers to analyze, day 1 and day 4 and say, oop, something is moving, and they're going to make alerts. And the number of new discoveries that are going to come out of this is amazing. So there are lots of visitors from very far to be discovered, and I think they're going to come up with some really neat things. Anyway, thank you very much. I'd love to have some questions. Thank you. I think Tom wants to use the microphone. Yeah.
Hi. Any further comments about Oumuamua? Can you hear me?
Yes.
Yes. Any further comments about that Oumuamua? Because Avi Loeb says that it's an artifact.
I'm sorry. Comments on Oumuamua? Yeah. Okay. They only could see it. Like, I'm very good at taking photographs of animals' tails as they're running away from me. So we were doing the same thing with this, that it was already going away. And when they had a run at a certain telescope where it was nighttime, and then they had to wait for another telescope further around the world as we turn, they found there was quite a significant difference in brightness on a cycle. And they figure that it must be tumbling. And if it's tumbling, it has to be 10 times longer than it is wide. Now, I don't know if that's the cause of the change in brightness. I mean, I honestly don't know, but that's a theory. I know one guy said, well, wait a minute, maybe it's a spacecraft from another solar system and they want to check us out. Wouldn't it be neat if that happened? But I don't think there's conclusive evidence of that. And I'm a skeptic, so, but good question. Okay. Have I answered your question or do you want more?
Well, he's a major astronomer.
Yeah.
He's a major astronomer, and he claims that it's an artifact from somewhere.
Yeah.
And I just want to know if you know if you could tell us any more about the controversy.
Well, I mentioned the one astronomer that said that, Comet Ison is going to be as bright as the full moon, and he got lots of publicity because that's a sort of snazzy thing. And I'm very skeptical that it is an artifact from another civilization, in part because if I were from another civilization, I think I would monitor the Earth by radios, and you can set up great big disks further out in the solar system and maybe go into orbit in the solar system further out, and they could watch I Love Lucy or whatever TV show they want to watch. So I'm very skeptical, but I don't think an awful lot of professional astronomers put a lot of weight into it, but I can't be sure. Okay.
Thanks very much for this. It made me think. I can't recall if a comet has ever hit the Earth. Has that been there's enough of them that one. Not sure that was a comet, but have there been any documented cases of a comet?
Okay.
As opposed to an
I
asteroid?
can guarantee with certainty that a comet has hit the Earth sometime in the last 4 billion years. But I don't know of any specific cases. There are some cases. I saw a talk at Toronto Center of somebody that there was a big explosion in Israel, I don't know, 1000 BC, something like that, near Jericho, right? And he talked about how it might have been something like a comet that exploded in midair. There's the thing that happened in Russia, I don't know, 1908, something like that. And it was an explosion, and you could see the trees were flattened out for a distance. But to my knowledge, there was no crater found. And it was a comet that when the heat of impact caused the whole thing to melt and just explode. So I think that probably was a comet. I'm not familiar with other cases, but I'm sure there being lots of comets. Okay. Great questions, boy. Any? Okay. Oh, good.
Are all comets made of roughly the same thing?
I'm going to give you the answer that I love giving my students. I don't know. To me, they would have to be carbon dioxide and water and some mud-like material. But are other comets different? As they do more research in comets, it could be they're going to find one with a slightly different composition. Maybe if we can identify a comet and get its orbit and say, oh, that traveled at the speed that would take us from Vega to us in, I don't know, 5,000 years. And Vega was at the time that it came from, so it probably came from Vega. And it could be we're going to find that the composition of the dust around Vega is different. And it could be that will lead to the fact that the composition of Vega is different than us. And maybe the Vera Rubin telescope will uncover exo comet coming. And we might be able to do the detailed experiments because, again, when Oumuamua was leaving, they could just get pictures of the tail. Okay, I'm sorry I can't give more detail, but that's a really good question. Okay. Oh.
Any more from the audience? Oh, Betty.
I was wondering how large comets are, and if there's a size where a person might say, this is not a large, this is too big to be a comet or whatever. It's something else. Is there a size limit on comets, or how large are they on average?
Okay. By some criteria, comets are the biggest thing in the solar system because the tail can be over an astronomical unit long, but it's pretty thin. The nucleus itself is sort of the size of a small town or a city, and some are bigger than others. Okay. But they're not very big. And I should know the comet that Philae landed on. I used to know the size, but I think it's something like 6 kilometers long, but I'm not sure. Maybe someone knows. Okay, Betty. Okay. Yeah. Oh, good.
Can you just tell us a little bit about an anti-tail, and if you could see it in a small telescope?
Can I give you some advice? Look at the Astronomy Picture of the Day website. And about 2 weeks ago, and I almost poached the image and I decided I wouldn't. They had a picture taken by somebody, and you've got this glorious tail that's nice and wide and a very thin anti-tail. Now, there's something that the comet has an orbit and it's in a plane of the orbit. Remember, I mentioned that. And the dust ends up not just being pushed right behind it, but spreading over the plane. And when we're just in the right orientation, we can, if we're here and the plane is looking at us, we can see an anti-tail. But it's very rare. And I personally didn't see it on this comet because it was cloudy for, can I swear? No, I guess I shouldn't swear. But it was cloudy for a few days before it cleared, and by then the comet had mostly passed. Okay, have I answered your question? What's that? You can see it with your naked eye. Okay, and this was just a hand, well, not probably on a tripod, but it was a camera that took the picture, and it's just stunning. Okay, did one of you have a question? Because I wanted to show something else if I could. Oh.
Yeah, and we got some questions online.
Oh, great.
Yeah, we actually have a comment from Brenda Shaw who says, Avery Loeb is a name that comes with a big grain of salt. It's not a spacecraft or an artifact, it's a natural object. She follows that up with, oh, and this is another one. I will continue to remind people that the guy who thinks he found Sodom and it was destroyed by an airburst is the dean of an unaccredited evangelical Christian college.
Okay. 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 Can I just talk about a tiny more thing? Okay. After I had it all ready, I noticed something in the news. And there was talk that people had found evidence for a planet 9. And it kind of relates to all my stuff on orbits. And I decided I'll just put a tiny bit together. So I don't think I'll be 2 minutes with this. Michael Brown taught a course that I took on the solar system, online course, and just fascinating. Oh, just wonderful detail. And he gets a lot of telescope time, and he looks at very deep images of faint patches of sky. And he then takes another picture, I don't know, 1 day later or whatever, or, like I did with Pluto, and he finds moving objects, and then he finds the details, and he's quite skilled at this. This from Wikipedia shows the discoveries in the far solar system, and it shows the 3 outer planets that are 10, 20, and 30 astronomical units away. And the periods are given in red, but it's hard to read. Outside Neptune, you have the Kuiper Belt, and the diameter gives the idea of how big the dwarf planet is. All right. So these are the objects, and what he finds is when they find the elements of the whatever the body's called, a planet or an asteroid. It's a planet if it's round, a dwarf planet if it's round. And from knowing the elements of it, you can work out that in this direction, say towards Antares, it's where the sun, if someone were on the sun, would see the thing at perihelion with Scorpio behind it. But then it takes its deep, deep trip into far, far away. It would be in Orion, which is the opposite end of the sky. So from these elements, you can work out where the comets, where these bodies go. And it turns out they're alleging for some of these, most of the objects are to one side. So it could be most of them are in the Orion direction and none in the Scorpio direction. Now, I don't know which direction it was, but I'm just saying. So what they're saying is maybe the reason there are no of these big objects in the Scorpio direction is that there's a planet 9 that is big enough to have disrupted their orbits and either shipped them into another place or whatever. And that news came out just yesterday. And this is their argument, but it's one of these things in science where it's not settled. And I love that, where they're still arguing back and forth, because some people think it's a new planet, some not. And they're trying to look where they think it might be, but it takes a lot of telescope time. Now, Eris is magnitude 18 and a bit. That's the biggest thing out there. So this might be magnitude 25, 26, and it's really stretching the ability to pick things up. So they might find the actual object, or it might be an argument in limbo. Anyway, I decided to add that in if there was time, and given that one speaker couldn't make it, I decided to add it. So anyway, if there are no questions about that, I'll let you get on with Frank's talk.
All right.
Okay. Thank you very much.
All right. Thank you.
That's where my glasses are.
And we're just going to punch in the live feed from the Carswell Observatory while we switch over to our next speaker. Just a quick note, there's no audio feed.
Oh, okay, great. Great. Good to see you.
Frank?
So what's this?
Remind me, Frank, I've got your coffee mug. Oh, you've already got it? Oh, good. That's when it comes to coffee, yes. Okay, well, I'll put it on there.
So you stay out of the way here? I'm going to stay out of the way. Will you do that?
But I'm really skeptical that it is a spacecraft.
All right, we're back. And our last speaker of the evening is Frank Dempsey, who's going to be talking about the Rask Toronto Centre Telescope Loan Program, recent additions, and some notes. Frank?
Okay, thanks, Tom. Sound check seems to be okay. And so just a very brief illustration here. I only set up 6 slides. It was intended to be a very brief announcement. And so in case you're not aware of the telescope loan program, I just want to point out that there are some telescopes that the Toronto Centre loans out to members upon asking, and there are several of them. There's some photographic imaging equipment as well, but it's not covered here. I'm only here to talk about some visual observing telescopes that I want to make a few details about. And they're illustrated here. So the Schmidt-Cassegrain on the left, I have at home. I lend it out. Dobsonian, I used to lend that one out too. I found another volunteer to handle it right now. And you see Coronado Solar Observing Scope on the right-hand side for looking at the sun. So those are 3 scopes I'm aware of for visual observing. If you look on the Telescope Loan Program website, there's actually an 80 millimeter refractor, but I don't know its condition or where it is. And I have to say very politely, the website is not perfect and it's not totally up to date and it's not 100% perfect. So I'm showing you what I'm aware of because I maintain these instruments. So that's the first slide. Some new additions that came in recently. I want to point out. The 8-inch Schmidt-Cassegrain or 200 millimeter Schmidt-Cassegrain you see there in the middle is another one that we got, and that's the one that I have. I've been loaning out for the past couple of years. I'd have to say it's quite a non-ideal instrument for a beginner who wants to use it. And some of the people who've loaned the telescope from me have been young mothers with daughters, maybe 10-year-old, 12-year-old daughters that are extremely excited about wanting to borrow a telescope. But this telescope is totally inappropriate. It's pretty heavy and it does take some muscle to handle it. If you don't have good back and shoulder muscles, then this might be a bit of a problem. And that's my impression of it. So I was glad to see when this scope on the left became available from Tony Horvatin a few weeks ago. It's a 4-inch f8, approximately f8 Newtonian, or actually it's a Dobsonian. You may be familiar with the Dobsonian, but point is, it's very light. It's a very excellent telescope made by Steve Dodson. You may or may not have known Steve Dodson that used to make these commercially. Made some really excellent telescopes, excellent telescope maker. This is a homemade telescope, as you can probably see. But the point is, it's a really excellent telescope. I'm looking forward to lending it out to people who want to use a telescope for the first time because it's lightweight, easy to handle, easy to point. It gives really sharp, excellent images. So I'm really excited about this. It's not quite perfect, so I want to point out a few little slight problems in another slide or two. The 8-inch Schmidt-Cassegrain you see in the middle, LX50, it would be good too. And its optical quality is superb. It gives really spectacularly sharp images. I really love it. There's a few little problems with it why it's not operational, and I'll have to do some work on it to get it ready. So it's not yet ready to loan out. I actually pointed out a few at the bottom right-hand corner where I pointed out that it's missing a star diagonal, which you basically need with a Schmidt-Cassegrain. And the other arrow on the left points out a broken bolt on the finder scope mount, which is not critical. So I can fix that in all day. So maintaining these instruments to loan out takes a bit of mechanical know-how. And so I'm not afraid to drill and tap holes in wood or metal and install a few bolts here or there or whatever it takes to do it. So you see this 5-inch Meade Newtonian pictured on the upper right. That tube came with a mount. A guy rescued it from the garbage. He said it was in the garbage, put out for the garbage on the curbside for garbage pickup next door or across the road from where he lives. Anybody want it? So I said, yes, I'll be glad to rescue it and fix it up and loan it out and donate it to the Telescope Loan Program, because I think a 5-inch Meade Newtonian is an excellent telescope for beginners or anybody. I'll show you why in a minute, why I'm slightly prejudiced toward 5-inch telescopes. But the focuser is broken. So you see, I put another one there I found from my collection right beside it. So I've put that into the picture too. So I have no problem replacing the focuser. I'm planning to get a mount. Somebody's going to donate a mount. So the broken equatorial mount that it came with is also not a problem. So I mentioned a slight problem with that Newtonian or Dobsonian. That is that although it's not pictured, it has a mount for a Rigel Quick Finder. So some of you may or may not be familiar with a Rigel Quick Finder. It's a very good pointing device. So the one that came with this one is broken, doesn't work. And it's not the sort of thing that you can take a screwdriver to and adjust and fix. It's a sealed little plastic unit. So I have a problem with that, but I'll mention what I want to do about that. Let's see if this works. I want to mention that if anybody has small telescopes like these, they want to donate or no longer using or don't know what to do with anymore, they'd be really useful in the Telescope Loan Program. So I put these pictures of my telescopes because I think they're really nice. So I have a lot of telescopes that are in the 4 or 5-inch range. So I just pointing out some. You see the one on the left is an 80 millimeter refractor. There's probably lots of them. Probably a lot of people have them lying around. They're not using them anymore, and they've replaced them with bigger scopes. And they said, "Well, this isn't worth much money, and I don't know any use for it." But I'm telling you now that it would be very useful in the telescope loan program to loan out to first-time telescope borrowers who don't have huge, strong, powerful back and shoulder muscles to handle a Schmidt Cassegrain. Anyway, I wanted to illustrate that's also a fairly old-fashioned manual equatorial mount. So that rig on the left is one that I use for put a solar filter on. I make daily sunspot observations with that. I've been using that rig for at least 10 years. It's really darn good. It's really darn useful, really easy to use. The arrow points to a block of wood. And so I can easily adapt any telescope from whatever onto, put a Vixen style dovetail bar onto it and a Vixen saddle or a base onto the mount by means of a block of wood. And really it's just too easy to attach it. So I can attach any old telescope to an equatorial mount that gets donated pretty easily. So I pictured also 102 millimeter Celestron Omni refractor. I picked that one up a few years ago, and I decided that's really excellent telescope. It's really darn nice. I see them advertised now for sale for less than $200 on the range of $100 to $200 for an optical tube assembly. I think it's phenomenally good telescope. So again, it's one that people might have lying around, not knowing what to do with, saying it's not worth much, but I want you to know that it's pretty darn good for a first-time telescope user. So it's pictured here on my Celestron CG4 mount. I think that's such a good mount. I happen to have 3 of them, and why is a long story, but the point is that's a good telescope to illustrate. You see on the upper right, 127 millimeter Maxitov Cassegrain. They're also fairly popular, I think, and so I don't think there are a lot of them lying around that people don't have a use for, because it's a really phenomenally excellent little planetary telescope. And let's see, that one in the middle, that's right about here, is was a junk scope that I got a hold of. It is a Meade ETX 90 millimeter, and it was in a cradle in a Schmidt Cassegrain mounting. So the mounting was no good. Hand controller was piece of garbage. So I took some bolts out, ended up with a tube. I put a dovetail base on it, as I briefly mentioned earlier. It's sitting on my CG4 mount, but it's got my Celestron zoom eyepiece in it. But the point here is that this little 90 millimeter scope, I was really shocked to find out what a super excellent telescope this is. It gives absolutely sharp, incredibly excellent images. And it's tiny, and it's lightweight, and it is easy for any beginner to use. So it's another one that might be small enough that somebody could have lying around in a drawer, broken, saying the hand controller doesn't work anymore, the mount is a piece of crap. It was pretty good maybe 20 years ago, but now it's a piece of scrap and I don't know what to do with it. And so again, I want you to know that the telescope loan program could put it to use as a telescope to loan out to beginners. One detail I want you to see on the lower right-hand image is a corrector plate for that telescope. So the arrow points out a spot. And so I know that a lot of older telescopes and eyepiece can get fungus type growth on the inside of the lens. It may be a coating deficiency where the coating is deteriorating. Maybe the coating is 30 or 40 years old. I don't know. I'm just taking a wild guess, but I've seen this on some eyepieces as well. So this spot here looks ominous on the corrector plate. However, despite that, this scope gives a really excellent image. You can't notice the spot. It might cause a slight decrease in contrast. Maybe if you compared it with a brand new one, you might be able to pick out, hey, there's a slight less, spot of a patch of less brightening in this little area. But overall, this telescope, despite its deficiencies, is excellent, really good. Okay, so that's telescopes that I just pictured my own as examples that you might have lying around, or somebody might have lying around, think it's junk and not of any value, but it'd be of great value to the telescope loan program. Okay, I mentioned a few little deficiencies. So you may be familiar with a Rigel quick finder. So the one on that 4-inch Newtonian is this one right here, in case you're not familiar with the Rigel quick finder. And as I mentioned, it's tiny enough. I can't take it apart. I can't really fix it like I could with this Telrad. If you're familiar with the Telrad, the point here of this picture is that if you have any parts lying around in the drawer And people may have these things and eyepieces and Kellner or Plossl eyepieces lying around in a drawer figuring out the junk, and I don't know what to do with them. But so have some telescopes, not enough eyepieces to lend out with them. Anybody has old, okay, so I don't want these ones, right? So some telescopes, don't bother with need one. Okay, so $30 or is it $29, and some telescopes, no, just keep them. I don't really want them, but I keep accidentally skipping forward to this slide. But go back to this one if we can do that. So the point was the eyepieces especially are sort of things that people may have lying around in the drawer figuring they're junk because if we replace them with some upgraded eyepieces, take your pick, Nagler's, Hyperion, etc. So anyway, the point is if anybody has eyepieces lying around, I think that they're not good. They're quite useful. I could use them with these telescopes. I pointed out the Rigel Quick Finder. So I'm just saying if anybody has one lying around not being used, I could put it to use immediately on that 4-inch telescope that needs one, that has a mount on it. I could also take this, I could also take this Telrad, which is my own. It's one of about 5 or 6 that I didn't get rid of, didn't sell a few years ago when I found out a good way to not need them anymore. So this one's cracked, broken, it's cracked, but it still works. And so I could put a base on that telescope and put this Telrad on it if I need to get it operational. So I'm not sure yet if it's a good idea for me to drill holes or do any permanent damage to that telescope tube, which is really nice. So anyway, we'll see what happens. Somebody might come forward and donate a Rigel Quick Finder that will replace it. Keep bumping ahead to that. I wanted to point out the Schmidt Cassegrain I pointed out that was donated recently has a few other slight little problems. I may have mentioned it, the hand controller is missing. I pointed out on the first slide, no star diagonal, and that's fine. I got a few of them. I could easily put one of my own on, and it's again, it's a sort of thing down here that anybody could have lying around in the drawers and figure, hey, I've upgraded mine to dielectric or 2-inch or whatever, and this is just lying around and there's no use for it. So finders also useful. The point about these bolts here is that if you're familiar with an 8-inch Schmidt Cassegrain telescope, the one that I've been loaning out for a couple of years has 3 of these bolts to go on the base. And so you set up the tripod, it's got a wedge on it. You take a bit of muscle and you hold that telescope and you put 3 bolts into the base of it, and then you slide it into the wedge. And it's fairly easy, so I've been able to train any of the telescope borrowers to do that. Even the very small ladies can do it without too much trouble. However, the new one came not with 3 of these thumb bolts, which are, darn it, not 3 thumb bolts, which are original equipment that came with that Meade. But this one came with a bag containing 3 half-inch bolts. One's a bit longer than the other with some flat washers for spacer and a half-inch wrench. And so I think it's a bit more of a stretch to train somebody borrowing that telescope to use for the first time to put 3 bolts in it and tighten them in with a wrench. It's a bit of a stretch. So I'm just pointing out these bolts that if anybody has these lying around for any reason, again, I can put them to use immediately if they're looking for a home. The other detail on this to illustrate is one example of a chart book I put in here. So anybody that has beginner's charts or beginner's books also lying around, and you want to donate, you think there's no use for it, again, I could put it to use. I could hand it out with those telescopes that I hand out to first-time telescope borrowers. So this one happens to be a Celestron Sky Guide map, which some of you may or may not recognize. Minor detail. If you have, there's a number of books that are pretty good for the purpose. Okay, anyway, I showed this one already. Say no thanks to some telescopes. Last slide. I mentioned telescope loaners in Toronto because I live in Pickering, and so I've had a number of people who've driven across Toronto from the west end of Toronto or beyond, excited to come and borrow a telescope, and some have said, "Oh man, do I got to drive all the way to Pickering?" And in my case, the answer, yes, do, because that's where I live. So I convinced one guy that asked that was a guy that has maintains the Dobsonian. I showed you the Dobsonian earlier, and I said to him, you know, one solution is if you could become a volunteer yourself and loan it out to whoever wants to borrow it, you'd have full use of it anytime it's not being loaned out. So he thought that was a good idea. So he took the job and he's on loaning out the job. But if anybody else wanted to do that, I'm saying there's a need for telescope loaners. It takes a little bit of time. You just respond to requests and you arrange to meet somebody somewhere. Train them. I find it takes maybe 10 or 15 minutes to train the person to set up the telescope and do it competently and sign a little bit of paperwork, and they have the telescope for a couple of weeks. We also need a telescope loan program administrator. That's because it's handy to have somebody starting to maintain, keep track of where all these scopes are at any one time, and also make official requests for more for the parts and telescopes that I mentioned. I'll be putting a few little notes on the forum in a couple of weeks coming up. I'm not willing to volunteer as the administrator. That's because I'm going to be taking some courses, starting to take some courses soon for a mathematics degree, and I'll be pretty busy. So there's some ways to contact us. You can contact me at my sort of email there, and you may try contacting the email on the TLP webpage of the Toronto Centre webpage, telescope loans, and it may work, but I pointed out that the website is not 100% perfect. So the current web administrator does a good job of forwarding on emails to us when he sees them, but sometimes he misses them, and so somebody can fill out the form to borrow a telescope, and it goes nowhere until the web administrator forwards it on to us. So there's some imperfections in place. So somebody could, if you have some stuff you want to donate, you could send it to the email address on the Telescope Loan Program website, but it may or may not get through. So you also have my email there as well. So that's all I wanted to say, Tom. And so don't think there'd be any questions. The point is, anybody who wants to donate anything, I want you to know that it would be put to use. Okay, thank you.
Any questions?
So if I wanted to loan out a telescope, how would it work? So I would come to you and email you and...
No, you look on the website. There's a
Okay.
Telescope Loan Program website on the Toronto Centre website.
Okay, I found it, yes.
And it shows these telescopes here, as well as a couple of other things. And so you fill out the form, and then you click submit.
So, and then do you know, like, how much is each telescope? Or is it free or...
Free.
Free?
Yep. It's a free service. I should have said that at the beginning. I should have given a better introduction. Telescope Loan Program provides telescopes free to members.
Amazing.
Thank you so
much.
It's amazing. It's for 2 weeks
Thank you.
or longer. Some have borrowed it for a month or longer. I think it's phenomenal because people who've never used a telescope before can get one as a benefit of membership. And it's the reason I request people to step forward as telescope loaners is because it's really good. It's a really good feeling to get somebody excited to see a telescope for the first time, get their hands on a telescope. Okay, glad you asked that question.
Okay, and seeing as there's nothing left, all right, we'll just quickly flip to fun facts, or sorry, the sky camera, and while we get the announcements up. Almost over.
We went longer. You.
It's a good thing we have this technical glitch.
I've got to get that recorded with Arnold. Okay, we're good.
Okay, and folks, okay, almost done. Just got to get through the announcements. Okay. So yeah, so for those of you joining us live and here in this, I can't really call it a studio, but I guess classroom, welcome. So this is one of two types of meetings that we have here at the Toronto Centre. What you've just seen is one of our recreational astronomy nights. And in 2 weeks' time, we're going to have one of our speakers' nights, in which case a member of the astronomical community will come in and talk about a subject that's near and dear to their heart. For those of you who are joining us live on the YouTube chat, please say hello. Please enter some questions for presenters, as others have already done. If you're a new member of the Toronto Centre, please introduce yourself. And if you're coming to us from far, far outside of the Toronto area, please let us know where you're coming from. So our next speaker tonight is on Wednesday, November 20th, 7:30 p.m. online only. Claude, let me apologize, I'm going to butcher this. Cournoyer-Cloutier, a PhD candidate in astrophysics from McMaster University, will be talking about stellar siblings, binary stars and star clusters in the Milky Way and beyond. So Wednesday, November 20th, 7:30 p.m. online only on YouTube. Our next recreational astronomy night is Wednesday, December the 4th, 7:30 p.m. online only. And the reason why I'll show you in a minute. Claudio Oriani will be talking about the sky this month, hopefully without the technical glitches that we just had this month. Rishi Nath will be talking about using N-body simulations to analyze transit timing variations in multiplanetary exoplanet systems. I have trouble saying that. Jeez. As I said, online on YouTube. Immediately following this will be the 2024 annual meeting of the Toronto Centre of the RASC. And this is why we've gone online for this meeting. So the agenda, the minutes from the last year's meeting, the slate of council candidates, and the proposed new bylaws have been posted to the website. You must register for this meeting by no later than midnight on the 2nd of December, because we need maybe 48 hours to make certain that everyone who's registered is actually a member. If you did not receive an invitation email and are a member of good standing, contact me immediately at president@rascto.ca. So the proposed bylaws I just mentioned. So the creation of the Ontario Not-for-Profit Corporations Act has required that we make some changes to our bylaws to reflect the new legislation. This was not fun. This was some bureaucracy we had to deal with behind the scenes over the summer. Paperwork. We have drafted a new set of bylaws and we present them for your approval. They are listed on, they are on the website and they are in the login required section. So when you click on the link, it will, if you're not already logged into the site, it will ask for your login. A call for nominations of the Toronto Centre Executive and Council. We have a serious problem, ladies and gentlemen. For the first time in history, Council has failed to provide a complete slate to the membership. We have vacancies for the first VP and for the secretarial roles. We have been beating the bushes for many, many months on this. We have begged and pleaded and cajoled people. We keep running into what are very understandable issues. People are too busy. People do not have the time. We've even gotten a couple of cases where folks have issues with their employer who doesn't like them working on the board of an organization. And the residing paperwork to get approval for that is just too much headache and they don't want to. So anyone wishing to join council, nominations are now being accepted for open positions. The member must be in good standing of the Toronto Centre and the nomination form requires the signature of 2 members. The deadline is Wednesday, November 20th at midnight. Please email all of your nominations to the secretary at rascto.ca. On that note, I regret to announce the resignation of Lucy Winicki as secretary. This occurred in the last couple of weeks. Lucy has been a hard-working core member of the Toronto Centre for a long time, and her presence is sorely missed. On a temporary basis, Ralph Chu has taken over as secretary to get us through the next few weeks. But the intention is that the hope and the intention is that when, after our annual meeting, Ralph returns to civilian life. Pray louder, Ralph. Okay, moving away from the paperwork. So, coming up as a City Star Party for members only, the Long Branch Park Pilot Project, the first clear night of November 23rd, 24th, or 30th, or the 1st on 8 p.m. So first clear night. So if it's clear on the 23rd, but clear on the 24th, nothing is happening on the 24th. Please check our website for a go, no-go decision based on the weather. I regret to announce that the DDO Astronomy Family Night for later this week, Happy Birthday Edmund Halley, has been canceled. So just getting that unfortunate news out there quickly. Coming up at the DDO for Astronomy Speakers Night on Saturday, November 16th from 7 to 9 p.m., June Parsons will be talking about the James Webb Space Telescope and the search for life in unexpected places. Registration fees are as seen here, and you can register online with the links can be found at rascto.ca. And then coming up on Sunday, November 24th, 12:30 to 1:30 p.m. is Virtual Sunday Sungazing. Registration fee is shown here, and again, the links are at rascto.ca. The Carr Astronomical Observatory is open. Conditions are largely back to pre-pandemic conditions. The only thing that we're doing is that masking in common areas is encouraged, but the preference of the people actually in attendance will be taken. You can see the online bookings page for more details at the website. Just a reminder, we run on clean, renewable volunteer energy. If you're a RASC Toronto Centre member and you've got some free time and you're interested in helping out, please drop a note to the volunteer coordination team at volunteer@rascto.ca. RASC Toronto Centre has paired up with Benevity in order to receive charitable donations. If you're a volunteer and your employer has signed up to make contributions for charitable work, let myself know or our treasurer at the email addresses shown here. It's that time of year again, plugging RASC memberships. Holiday season is upon us. Gift memberships are a thing. You can renew your membership. You can sign up online at secure.rasc.ca, and gift memberships are available from the national office at mempub@rasc.ca. Oh my, hang on. We have one very important slide that unfortunately got skipped over. Just give me one moment. Or not. Yes, the meeting after the meeting. So we'll be heading over to the Fox and Fiddle Pub, which is at 1285 Finch Avenue West. That's a block east of Keele and Finch on the south side. It's right next to Finch West subway station. What that means is that one quick subway stop over, and reminder that with your Presto card, you've got a 2-hour limit before you can get back into the system, and you don't have to pay again. So you should have enough time to have a pint. There's also free parking. So if you drove over. Anyway, so 1285 Finch Avenue West. We're giving these folks a try. We are still trying to find our new home away from home for meetings after the meeting, because we're a little too far away from our old stomping grounds of the Granite at Eglinton and Mount Pleasant. So we're going to be heading right there. We're heading over right after. And on that note, I'd like to wish you all a very pleasant evening. Thank you very much for joining us. Please follow us on all forms of social media that we've got listed here. If you've liked what you've seen live on YouTube, please like and subscribe and hit the notification bell. Be safe and keep looking up. Good night, everybody.